Good morning, everybody. Setting up things a little bit differently this morning. I'm going to talk a little bit about some acceleration topics. And then I'll answer any questions you might have had about the learning guide from last day. But let's start with some green check marks so I know you're with me. And then we'll do a couple little, I don't want to call them experiments, but think of them in terms of thought experiments maybe. Exercise your brains first thing. So while you're doing this, we'll have like just a couple minute break here in a couple minutes just so we can fix the studio, and then if you wanted to put any questions in from the learning guide, I'd be happy to do those. So good. Last day we were talking about acceleration, we were talking about change in velocity, and the definition of acceleration is the rate of change in velocity. So if you have your velocity changing from 0 to 10 meters per second, if it changes really fast, that means you have a big acceleration. If it changes really slow, it means you have a lower acceleration. So everything we talked about were cars speeding up, slowing down, people on skateboards, things like that. But what happens if we were to talk about things that are falling? So I have this dry erase marker from my office. If I drop it, what happens to it? What are we saying is going on there? Is the object traveling at a constant speed until it hits the ground? Is it speeding up as it falls? Is it slowing down? How do we describe the motion of something that's falling, an object that's in free fall? And we could talk about its change in velocity as well. The important idea here is that if I drop something, what's its initial velocity? I know I'm throwing a lot of questions at you here. Just trying to get you to think a little bit. So there's some good stuff coming into chat here. Is it speeding up as it falls? Is it a constant speed? Doesn't it go faster, longer because of gravity? These are all the answers I was looking for. So first of all, gravity is what we're talking about. Why does something fall towards Earth? Well, Earth has a gravitational field that's very large, and objects that have large masses will be pulled towards one another because of gravity. So we think of gravity as only existing in, in the scale of like planets and things like that, but everything has a force of gravity. Everything creates a gravitational field. If it has mass, it has a gravitational field. So essentially, me and this pen, we both have a gravitational field. It's really, really small compared to the gravity that's created by Earth, but we do have a gravitational field. And on really big scale, so if you think of the largest things humans kind of can create that move, and like buildings can't move, but super tankers and big boats and harbors, they have so much mass, they're so massive, that if you park two really large boats really close to each other in a harbor, their forces of gravity will actually pull them together. And the force that brings them together is actually really small, but it has been documented. So everything has gravity, but it's just the Earth has a strong, strong sense or force of gravity because it's so large. So what you guys are putting in chat's good. Ava, you asked a question, is it speeding up as it falls? And then Abby also said, doesn't it go faster? Does it speed up, or is it going the same speed? I mean, if I drop that, it's kind of hard to tell in this small little time frame that we have here. But I will tell you this, that anything that's falling towards Earth will continue to accelerate until it hits Earth. We run into a bit of a problem. And if you think about somebody who goes skydiving, does anybody know the word that we refer to that the thing that stops people from continually going faster and faster and faster? Does anybody know what that's called? For objects in free fall? I don't see anyone typing. It's called terminal velocity. So if you were a skydiver, you jump out of the plane and you're flying down towards the ground, you reach terminal velocity. And that means that essentially the force of the air pushing up on you is equaling out to the force of gravity pulling you down, and you can't go any faster. the one really tricky thing that not tricky, the really great thing that we deal with in physics is we ignore air resistance. So for the sake of all the sorts of questions we do, we don't have to worry about the resistance of air pushing up on things. All right, another question that I like to ask is, if I have a sheet of paper here, 2 sheets of paper, if I drop these sheets of paper, what happens? Let's just try it here. They kind of fall down, they move around a little bit. Now, what happens if I take one sheet of paper and leave it like a sheet of paper and take another piece of paper and I crumple it up? These are the same pieces of paper. Now what happens if I drop them both again? What's going to go on here? What do we think? They fall slowly. I like that. What would happen now if I drop them? Happy's getting on the right track. So we're dealing with surface area. Essentially what I've done is I've decreased the surface area of the object. So which one is going to hit the ground first? This is kind of the important thing here. One's more dense, so it'll fall faster. I want to be careful with the word density because it's paper. It has the same density. So I don't think you mean density, but we're talking about surface area. They're identical pieces of paper. They have the same density. The only thing I've changed is the surface area. So I'll drop it, and you guys kind of guessed properly that the paper would fall slower because of air resistance. All right, let's continue that. I have a textbook here, and I have a piece of paper, and they have the same surface area. They're the same shape. They're both 8.5 by 11. So you guys all said, well, surface area makes the crumpled up one fall faster. So if I drop a piece of paper and a book, you've told me that these have the same surface area. Shouldn't they hit the ground at the same time? Taylor's on it. It's heavier. Well, that's an interesting idea. More gravitational pull for things that are heavier. Interesting. I'm not sure. Let's find out. Let's drop these. All right, so the textbook hit the ground first. All right, you said that the textbook was more massive, so it had more weight. It was heavier, so it hit the ground first. And is that the real reason it hits the ground first, or am I just kind of playing with your brains now? What if I can't obviously make this piece of paper weigh the same as this, but what I can do is kind of take away some of the air resistance in the room. Now, I don't have magical powers to suck all the atmosphere out of the room, but what I can do is this. If I drop these and they're side by side, the book's going to fall and hit the ground first. What if I take this piece of paper and I put it on top of the textbook? Like that. Now they are together. What's going to happen if I drop this? Is the piece of paper going to fall more slowly? Or are they going to fall at the same time? Is the paper going to do its waving back and forth as it goes to the ground? You said that the textbook has more weight, so it's going to hit the ground first. Is that going to be true in this case? Shall we try it? See, everyone's feverishly typing. Fall faster because the textbook pushes air away? Maybe. Well, I don't know. Let's find out. So you can see that, I'll do it again, just in case you weren't watching or didn't see it very clearly. If I drop them separately, the textbook falls really fast and the paper kind of floats down. If I put the piece of paper right on top of the textbook, basically what I'm doing is I'm removing air resistance from actually hitting the paper. And if I drop it, I'll drop it again here. You can see that the piece of paper hits the ground at the same time as the book, or it doesn't, float down like it did before. So basically, what I've tried to show you is that the idea is Surface area plays a big role in how fast things fall. But in physics, we ignore surface area. We don't care. It doesn't have any effect on our problems. I shouldn't say it doesn't. We ignore it just to make the problems more straightforward. So then we got to the idea, well, things that are more massive, things that have more weight are going to fall faster. Well, is that the case? No, it's not the case. These have completely different masses. This textbook maybe weighs like, I don't know, 500 grams or so, and this paper, only weighs 1 or 2 grams. But if I put the paper on top of the book, it hits the ground at the same time. So according to our kind of guesses here, things that have more weight fall faster. That's not true. That's not the case. It comes down to air resistance when we drop things. And in physics, all through grade 11, all through grade 12, even through your first year of university, and even through most of second year university, you're going to ignore air resistance. Air resistance is really, really hard to do calculations with, and you have to learn calculus in order to do it. So we just ignore air resistance altogether for objects that are falling. Another important thing here is that these objects aren't falling at a constant speed. They're speeding up. So as they fall, they're going faster and faster and faster because they're accelerating towards the ground. Gravity causes things to accelerate. So if we were to ignore air resistance, imagine a skydiver was falling towards Earth and there was no atmosphere on Earth. Maybe we pick a different thing, like the moon has about 1/3 of the gravity of Earth. If you were to have a magic skydiving plane that could fly to the moon, you jumped off, you would continue to accelerate towards the surface of the moon until you either hit the surface of the moon or maybe you had some sort of fancy rocket ship that slowed you down. So objects will continue to speed up as they fall, and we're going to ignore air resistance altogether for all of our problems. So I'm going to just leave it at that for now. I'm going to put up a few questions here in a second. Why don't you guys just think about them, and we're going to rearrange the studio. And then if you had any problems from the learning guide that you wanted me to go through, you can throw those into chat. And when we come back here in just, like a minute, we can go through those. So throw them into chat. I'm going to put up a few questions. We're going to rearrange everything, and then we will continue on. Thanks. All right, guys, sorry about that. We needed to get my computers and stuff out of the way and the camera, and it's a lot of work. Only one little studio here, we got to make the best of it. Yeah, Abby, either units 9 or 8, anything that came up. I see, Taylor, you've put in a question, so we'll talk about that. And anything, I know, Ava, you had asked about the question. I have it here in the Unit 8 Learning Guide, the last one, from the second half, number 5, E and F. Those are both fairly tricky questions, so I definitely want to go through those. But first, I can do this one for you here, Taylor. So this is page 5, number 13. This is from the Unit 8 Learning Guide. And basically, it's asking us to find the average velocity. It's given us a distance and a time. So we went to our formula sheet. We looked at the formula that had average velocity, distance, and time. And we can see that we can just use the information here. The 60 kilometers is a distance, so I'm going to put that on the top. And then we have 3 hours. I'm going to put it on the bottom. 60 divided by 3 is 20, and that is going to be kilometers per hour. Now, we don't have anything in terms of a direction at all, so we can just leave it as 20 kilometers per hour. And that's it. That's all there is to that one, number 13. Unit 8, 7F. 5, 7F. So from the first part, I'm going to assume 5F. Thank you, Eva. The last question. I wasn't finding a 7F. All right, so this is from the graphing motion section of the velocity. And Abby, I'm really sorry that I haven't marked it yet. I usually turn on the notification when students submit it so I get an email, and I just haven't gone in to look at it or turn it on. So I'll mark it as soon as we're done class here today for sure. All right, so question number 5 is talking about this graph here, and we can see it's a position time graph. We have position up here at the top, time down here at the bottom. So we know that we're dealing with position in meters, time in seconds. Maybe I'll ask you this. Ava, did you get letter E? Did you do that one correctly? Did you get the right answer for E? Because doing the last one is the exact same process. And I guess I kind of alluded to this last day that there's more than one way to think about these problems. There are more than one sort of method to do them to get the right answer. And essentially, it doesn't really matter how you do it as long as you're getting to the right spot. Perfect. Maybe I'll put you on the spot, Ava, and I'll ask you how you did E, and then we'll maybe do the same process for letter F. It just kind of is a bit confusing when we get to F. So for letter F, it asks for the average velocity of the car for the entire trip. And letter E is the average velocity between 0 and 20 seconds. So they're both asking for average velocity. Yep. Perfect. All right. So average velocity formula, V average, is the change in position over a change in time. And because these are both asking us to find the average velocity, we're going to do a change in position over a change in time for both of them. So the first one, letter E, asks us between 0 and 20 seconds. So if I just scroll up to my little chart here, I'm trying to find the average velocity for my graph between 0 and then 20 seconds is right here. So I'm trying to find the average velocity between 0 and 20. So the kind of the highlighted portion there. Now, there are 2 ways I can think of doing this question, and normally the way that I would do it is kind of a really long way, but it's the first thing that kind of pops into my head when I see this. If I want to find the average of anything, I'd add them all up and then divide by how many there were. But in this case, it's a little bit different because I'm dealing with velocities. If you want to think of a trip, I know I used this example before, but if you're driving from here to Vancouver, or let's say from here to like Chilliwack, you drive really slow at the very beginning through Kelowna and West Kelowna. And then when you got on the highway, on the connector, you drive really fast. So if you were doing 10 kilometers an hour and then you're doing 110 kilometers per hour, well, you're not going to add those two and divide by 2. You're going to say, well, I traveled the 10 really for a short amount of time, and then I traveled 110 for a really long amount of time. So when you're finding average velocity, you need to kind of think, well, there was that, a long period of time where I spent at that really high velocity and that really short amount of time I spent at that really low velocity. So how am I going to kind of average those things? Now, you can take how long you spent at each speed and then, kind of think about it in terms of your entire trip. And let's say you traveled half the time at one speed and half the time at the other speed. Well, you could average those out. But that seems kind of confusing here. So what I will suggest is this. When we find the average velocity, we want to take our change in position and divide it by our change in time. So if I draw a little red line, if I found a red line, draw this red line in here, this is the slope between these 2 points. Now, does it matter that my velocity changes between those 2 points? It turns out that it doesn't. And I'm just reading what you have here, Ava. Found the average velocity between 0 and 10, then I found the average velocity between 15 and 20. Didn't really have to find it for 10, 15, so it was 0. And I combined the velocities and got 2. Yeah, so I think that makes sense. I mean, you come up with the right answer, that's a good thing. What I will show you is maybe just kind of a really simple way to do it. And I think this is kind of what Abby was alluding to here. When I have my formula, average velocity is a change in position. So if I have delta D, that's going to be D final minus D initial. It's your change in position divided by your change in time. So let's change my formula a little bit here. df minus di over tf minus ti to make it look like the slope formula, because that's what we're doing. We're finding the slope of this red line that I've drawn up above here. All right, now I'm going to plug in some information that I know. My final distance, if I look at my graph, my final distance, sorry, that's time. My final distance was 40, and my initial was 0. So when I plug these numbers in, my final was 40 meters, my initial was 0 meters, and then time. Well, how long did it take me to do that? It took me 20 seconds was my final time, and this is 0 seconds was my initial time. So I'm going to go 20 seconds minus 0 seconds. So all I've done is I've got these 2 red points. I'm finding the slope, essentially, between them. I have one point here, this is 0, 0, and I have another point here, which is 20, 40. 2 points. And instead of x1, x2, y1, y2, I have t1, or t initial, t final, d initial, d final. So I do this. 40 minus 0 gives me 40 meters on the top. 20 minus 0 gives me 20 seconds on the bottom. 40 divided by 20 is 2 meters per second. And that is how we did that. It is exactly the slope in math, Abby. We've just changed the letters from x's and y's to d's and t's. The important thing is to remember that to find the average velocity from a position time graph, you just need to take the slope. The only thing that makes these 2 questions a little tricky is because they're asking for different points. And essentially, those points are the same as the points we would have dealt with in math. I've kind of skirted the question of letter F here. I'll talk about that now. So it's asking us for the entire trip. Now, if I go back to my graph here, there was nothing that required this position time graph to start here at the origin and end here. This line could have conceivably stopped here, or it could have stopped here. It was just the way the graph was drawn. It started on the x-axis and it finished on the x-axis. That wasn't by design, it was just kind of by chance. So don't think because this graph starts here and goes up and across and down and back over, it has to end here. That's not the case. The graph could have really ended anywhere. Could have ended here, we could have just ignored this bit. It didn't. It ended and started on the same horizontal line, which does some strange things to our math. Maybe not strange. I'm going to do the same process. It asked for the entire trip, so the trip started here and it finished here. And then I'm going to draw a line from one point to the other. And then I'm going to label my points just like I did before. So this is 0, 0, and this is 0, 45, 55. All right. Now I'm going to plug these into my slope formula. Which is going to look a little bit strange. So we're going to go d final minus d initial over t final minus t initial. And my final distance was 0 meters. My initial distance was 0 meters, or position I should say. My final time was 55 seconds, and my initial time was 0 seconds. So I'm going to end up with 0 meters on the top and 55 seconds on the bottom. Okay, what is 0 divided by 55? Well, that's just going to give me 0. So it turns out that my average velocity over this entire trip was 0. How is that possible? How can we, drive somewhere and taking a trip? How can we just end up with 0 velocity? Does that make any sense? How is it possible that we can end up with that? Because I get this 0 and I'm kind of scratching my head thinking, well, how did I end up with the 0? That doesn't really make sense. I drive somewhere, I'm moving, and how do I just have 0 velocity for the whole trip? I guess the important thing is this. If we look at the trip, it's important to note there's a few things going on here. I have a positive slope here, I have 0 slope here, I have a negative slope here, and then a positive slope here. So velocity does have a lot to do with displacement. In fact, the definition of velocity is your change in position or your displacement divided by the time it took. But one really weird thing about my trip is this. It's not like a regular trip where I just drove somewhere and then I took some turns and things like that. What's going on is the slope of my line is my velocity. So if I look at the first little portion here between 0 and 10 seconds, I have a positive velocity, so I'm moving forward. And then I have this horizontal bit up at the top where I've stopped, I'm not moving. And then I have this really long bit here in the middle where I'm actually moving backwards. I have a negative slope, so I have a negative velocity. So it's not like a regular trip that I'm just driving around, always moving forward. In this example, I have a positive velocity, I have 0 velocity, and I have a large negative velocity, and then a little positive velocity at the end. There's a second way you could have done the problem, and this is kind of what Ava had written up above. I could look at each of these velocities, so I could find the slope of this section, 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 and then I could multiply it by how long I traveled at that, or with a fraction of the entire trip I traveled at that velocity. And I would end up at 0. So I would say, okay, this slope is 6, this is -4, this is 0, and this is, 2. And I'd say, okay, I traveled at 6 for 10 seconds, I traveled at 0 for this long, I traveled at -4 for this long, and I would average them all out, and I would end up with 0 as well. So that's kind of the thing with physics. There's always, not always, almost always more than one way to do these problems. So just kind of whatever makes the most sense to you, just go with it. And Ava, what you wrote up above for the from between 0 and 20 was the same thing. You could have used that same sort of process to find the average velocity over the entire trip. But you could just draw a line connecting your 2 points, find the slope, and that'll also work, because position time graph, you can find the average velocity. Just while we're on the topic, just to kind of, we've looked at this specific example, but maybe extend this question a little bit further. If the question asks, what's the average velocity between 5 seconds and 35 seconds? What I would do is I'd say, okay, 5 seconds is right here. Here's a point. And then 35 seconds is right here. Here's another point. And I would draw a line between my 2 points, and I'd find the slope of that line. Now, it's a negative velocity, it's a negative slope, it's going down and to the right. So that's fine, this process is exactly the same. Just because I don't want you to kind of fixate on this entire trip is 0 average velocity. It's just kind of the way it worked out. So we could ask any 2 time intervals. You're going to find the coordinates essentially. So this is going to be 5, and this looks like at about 30. And then I'd go down here, and this is 35, and that's looking like negative 20. And I would do the same process. Y2 minus y1 over x2 minus x1, or in this case, d2 minus d1 over t2 minus t1, or find the slope. That's the average velocity between those 2 points. So you can do it for any 2 points on the graph. There we go. I didn't see any other questions in terms of the learning guide for Unit 8. Hoping you guys should be done that by the end of the day or tomorrow. Today's Wednesday, I suppose. Should be done this stuff. Test should be written by Friday. That gives you a day to polish this off, and I will start marking those learning guides right away. I want to just jump back into the notes and continue and finish off the Unit 9.1 and then jump into 9.2 for sure, Ava. Number 2 for Unit 9. So this is Unit 9 learning guide. Are we talking about on page 1 here? Make up a sketch of what the pool balls photos would look like if we were accelerating positively and negatively. Yeah, okay. All right, so if the pool ball were to accelerate, that means it's traveling a greater distance in the same time interval. So if I have my pool ball, you can see here it's at very regular intervals. The flash happens. The distances from here to here is the same as the distance from here to here is the same as the distance from here to here. Now, if the object were to accelerate, that means it would travel a greater distance. So what we're going to have to do is space out the balls, make them further apart in the same time interval. So if I have a ball here, and a ball here, and a ball here, those are all kind of the same distances apart, roughly, according to my fantastic drawing skills. Now if it starts to accelerate, I'm going to have a greater distance between each time interval. So these are roughly the same. We'll call them D. That's D. And then this isn't D anymore. It's a little bit larger of a distance, and then it's even larger here. And then it's even larger here. Again. So that would be an object that would be accelerating. So that's accelerating. The second part of the question asks a negative acceleration, or something that's essentially slowing down. So I'll pick another color here. So if I have my objects that are at regular sort of distance intervals, if the object's slowing down, it's not going to travel as far in the same amount of time. And remember, each time we draw that object or the flash of light develops the film, the object is going to be slowing down, so it won't quite get as far. And then if I were to draw another one, it would look like that. And I eventually would have these things all drawing on top of each other. It's really hard to see that. Space them out a bit more. All right, so there's an equal distance for those things. Then I'm going to draw this one a little bit closer together. And then I'm going to draw this one a little bit closer together. And then I'm going to draw this one a little bit closer together. And then the next one would maybe overlap it a little bit. And then we'd eventually end up with a big jumbled mess where all of the circles are on top of one another as if the object had completely stopped. So that's kind of what we'd end up seeing. There we go. I will jump into the notes, and then we'll finish these off. And I hope to get done the course today. I think we'll just fly through this, and if you guys have questions, speak up. If you don't have questions, that's okay. The stuff can get a bit tricky, so some of the problems can get more difficult once you get into the acceleration type questions. So I gave you guys these questions just as we transition. Can the acceleration be positive, but you are slowing down? Can we think of a situation where our acceleration's a positive value, but you're slowing down? How can that happen? This is kind of these confusing things where we start to think of signs. And I guess wrapping your brain around it's kind of the hardest bit. Remember that the sign just indicates direction. So if I have a positive value, then I could say that's forward. If I have a negative value, that's backwards. So I want to think of a scenario where I have a positive acceleration, but my velocity is actually decreasing. Is it possible to encounter that? What if I were walking backwards and I started to slow down going backwards? Would that fit this example? So my acceleration's positive. I'm slowing down going backwards. That means I'm speeding up in a forward direction, if you want to think of it that way. So if I was moving backwards, maybe you're in a car in reverse, you're moving backwards, but then you put your foot on the brake, that means you're accelerating essentially forward, or your change in velocity is going to be positive. So you have a bigger forward acceleration, slow down, but still have a positive acceleration. I'm not completely sure because I find this stuff confusing. It isn't sort of confusing, it's very confusing. So example one, if you're moving backwards and you slowed down, you would have a positive acceleration because your change of velocity would be positive. And then you would be slowing down. Can the acceleration be negative but you are speeding up? Can we think of an example of a situation where our acceleration's negative, but we're going faster? It doesn't say anything about direction. It says speeding up. So that could be speeding up going backwards, or it can be speeding up going forwards. So example 2, if I was in reverse, that means my velocity is negative. That's fine. And I put my foot on the gas pedal. Is my acceleration negative or positive? Well, because I'm going backwards, and I'm saying everything backwards negative, so I'm traveling in reverse in my car, put my foot on the gas pedal, I speed up going backwards. Does that fit that situation? Yeah. My acceleration's negative because all negative acceleration means is just opposite acceleration to the direction you're moving. Or I shouldn't say opposite. Everything backwards is negative, not opposite. So if I put my foot on the gas while I'm going backwards, my acceleration's negative because everything backwards is negative, and I'm speeding up at the same time. Car's initial velocity was negative 20, so I'm going backwards at 20. And the car has a positive acceleration of 5. What's the velocity after 10 seconds? That means my velocity is going to increase by 5. Every second. I'm going to jump over to here and let's do this one. All right, so I'm going to draw a car. Here's my car. That's a beautiful looking car. So the car's initial velocity was negative 20 meters per second. So it's going backwards. Hard to tell which is the front of my car and the back, but I'm going backwards at 20. The car is going to accelerate at 5 meters per second squared, or it's going to increase its velocity by 5 every second. 5 meters per second every second. So, okay, let's think of this. We're going to do this kind of two ways. If my car was initially going at negative 20 and 1 second passed, painfully difficult to read that. After 1 second. How fast would my car be going after 1 second? If I started at negative 20 and then I'm saying I have a positive acceleration. That's exactly right, Abby. I'd be going negative 15 meters per second. Okay, what about after 2 seconds? I'm going to develop a bit of a pattern here. So every second I'm changing my velocity by 5. So after 2 seconds, I'm going to change it by another 5. And I'm going to be going negative 10 meters per second. Okay, if I continue this on, what happens after 3 seconds? Well, I'm increasing my velocity by 5. What about 4 seconds? This one's kind of weird. After 4 seconds, my velocity is now 0 meters per second. How is that possible? What does that mean? What's going on? So confusing, Mr. Borden. All right, so we started at negative 20, and we're accelerating forward, but we're moving backwards. That's fine. That just means we're slowing down going backwards. So after 1 second, we're down to 15, 2 seconds, we're down to 10, then negative 5, then 0. What happens after 4 seconds? At 4 seconds, I'm going 0, so I've stopped. But I'm still accelerating going forward. So after 5 seconds, what is my velocity going to be? What happens at 5 seconds? That's right. Now my velocity is going to be 5 meters per second, but it's positive now, and I don't need to write in the positive sign. So what does this look like? Well, I'm moving backwards really fast and I start to slow down. And at 4 seconds, I've stopped, but I'm still speeding up. So I'm moving or accelerating forward. So that's a kind of a way to think about it. And then after 6 seconds, I'm at 10, 7 seconds, I'm at 15. Do I have to do this big, long list of things? No, I can use formulas to figure this out. So if the car has a positive acceleration, what's its velocity 10 seconds later? So I'm trying to find the final velocity, or the velocity at 10 seconds. Okay. Now, I don't necessarily, I know I have all these formulas on the back of my data book, and I need to figure out which ones I need to use. So these are all my equations of motion here. Now, I've just said I'm trying to find the final velocity. And the only formula I have here that's solved for final velocity is, it's just this change in velocity formula that's been rearranged to isolate or solve for VF. So they've just moved VF to this side and V to this side, or delta V, to end up with this VF. So we want to use this formula here. The final velocity is the initial plus the change. So I'm going to jump back over to here. I know my final velocity is my initial velocity plus the change in velocity. Now, I don't know a lot of things, so I'm going to have to use another formula. I know my initial velocity. That's given in the question. It says the initial velocity is 20. So the initial velocity, maybe I'll fit that in here, VI is negative 20 meters per second. Do I know my change in velocity? I don't. I don't know what I changed my velocity over that time interval. But I could find it because I know my acceleration is the change in velocity divided by the change in time. Or, if I jump back over to my formula sheet, what do I know? I know my time, I know my acceleration. I'm trying to find the change in velocity. So essentially this is a two-step type problem. And this is kind of why physics gets confusing. So my change in velocity is my acceleration times my time interval. All right, I don't know what change in velocity is, but I want to find it. My acceleration was positive 5 meters per second squared, and the time that I accelerated for was 10 seconds. So my change in velocity is going to be 50 meters per second. Okay, let's think about it this way. I know my velocity increases, it changes by positive 50 meters per second. If initially I was going backwards at 20, and I know it increases, or my change was positive 50, what should my final velocity be? I can think about it in my head, or I can plug it into my equation up above here. So I don't know what my final velocity was, but I'm going to find it. My initial velocity was negative 20, and I know my change in velocity was 50, because I know I was accelerating at 5 each second. So negative 20 plus 50 is going to be 30 meters per second. So my final velocity is 30 meters per second. Holy cow, Mr. Borden, that was a lot of work for one problem. Yeah, that's about as tricky as they can get, really. It's kind of a two-step sort of process. I can understand why you would get confused, Haley. First time you've seen a problem like this, we'll look at a few more, but it is confusing stuff. We'll look at a few more, and hopefully you'll kind of we'll get it. There's a bunch of problems like this in the learning guide, kind of two-step problems. We'll do more. This is just an introduction to it. So we'll leave that there for a second. I want to jump back into the notes. We'll just polish off the notes here, and then we'll do some more problems like that. All right, so that was this example 3. The next one jumps into acceleration due to gravity, and we talked about this at the very beginning of class. We said gravity's force is pulling between two or more masses. We talked about air resistance as something we just ignore for physics in grade 10 and 11 and 12. Just ignore